Start from the end of Wasim's beautiful talk, and then talk about a different topic, but still on making connection between theory and experiments in cold atom systems. How do I change page here? Oh. These keys don't work.
Oh, they should. Yeah.
Okay. So this was done by Reza Nour-Afghan and three of my students, Alexis Rimbaud, Charles-David Hébert, and Simon Bergeron. And the motivation, as you saw, is this resistivity that was found. I mean, this is a funny plot that I won't have time to explain, but that okay. Oh, they don't see me.
You can use the mouse cursor if you would like.
Where is it?
So with the touchpad.
Okay. Okay, it's unfortunately a very small mouse.
There might be a way to make it a bit bigger. Like if you go down to this corner. Yeah, so if you click on that pen.
On the pen,
yeah. There it is.
Okay. Nothing happens. So perhaps right click. I'll let you do it.
I'm not good with Macs either, so do left click or right click now?
It's small, but I'm the second oldest here, I can see it. So.
Okay, highlighter, would that be that? No, right? Just use the mouse. Okay, shall we?
Okay, okay. Let's do that. Okay, so it's found that resistivity is linear in many correlated systems. Where is my mouse? I don't see it. Okay. There it is. Okay, and that the scattering time that's deduced using this Drude formula is related to KBT. So let's say in cold atoms and high temperature, you've seen this plot. So the blue line is the calculation with finite temperature Lang's method, and the one that disagrees with experiment is dynamical mean field theory, which, as you know, is very unusual in this conference, right? And it's very dangerous to say. So first must be an error with the calculation. So we go back. There many people have looked at this this problem. So is there a kink, as we find here? Well, in fact, there is. I mean, this is a beautiful paper by Antoine and Gabi and the group, and you see that the resistivity does have a kink like we find here, and it has this linear temperature dependent. Oh my goodness, this is the worst. Okay, and this is what Edwin will tell us after in the next talk about these calculations from the Stanford group. So what can be the source of the disagreement? Well, it's very hard to, I mean, to blame it on anything else, but you see the mouse disappears when I try using it. I'm sorry, I'll just use the pointer.
Let me try this.
I'm sure you can guess where we'll go. So the vertex corrections that are absent in the dynamical mean field theory.
Okay, can you try this one second?
No, the thing is that as soon as I stop, oh no, okay, it stays. Okay, this one stays. So you see all the methods agree for what is the local self-energy. And if you look at the numbers here, the first nearest neighbor self-energy is much, much, much smaller. And so from this, you would say that vertex corrections are small, but in fact, how do I change page? Okay, so, but in fact, I don't have time to discuss this in detail. You can ask questions, but the group by Vucicevic and company have argued that the origin of the problem is vertex corrections. There's another method that you can use to compute resistivity in a funny regime. It's I mean, two particle self-consistent method should not be valid in this regime. The mouse is frozen. Yeah. So And you see that these are the experiments, these points there. And this is the result of the dynamical mean field theory. So with two-particle self-consistent approach, we get the wrong slope. It's not expected to be accurate in this region, but the point is that when we put vertex corrections, we don't see any difference. So that's still an unsolved problem in this area, I would say. You don't want to change page.
Let me try to restart. Okay, let's try once again then.
Okay.
And if this doesn't work either, is there an expert on max?
So the finite temperature Lanczos method claims to have explained the linear resistivity, and they do. But on the other hand, if you look at the width of the Drude peak, the experimental results are these orange symbols, and the DMFT are these green symbols, and finite temperature Lanczos method is this.
So people are going to say that they have measured the altitude of the peak.
Okay, you remember there was this hydrodynamic equation. Yes. So this gamma comes from the hydrodynamic equation. So you can think of this as the relaxation rate. It's indeed extrapolating to say that it's the Drude rate.
Okay.
Okay, so the conclusion is that not everything is explained in this experiment, and we need to work out a little bit more of the theory. Now, the perspective about this linearity, here I would like to point out that the magic angle bilinear correctly, the result of our quoted for linearity temperature, are in fact, this temperature is of the order of the Fermi energy. So these are really high temperature experiments, whereas in condensed matter, we're usually interested in very low temperature of that scale. So these are results on Q rates, and this is the plot I showed you before. KBT is much less than the Fermi energy. So are there models that give that at low energy, low temperature? Yes. I mean, for example, there's this modified upward model with long-range interactions.
Excuse me.
Yes?
Please say it's closer to the microphone.
Yes. Okay. I tried to speak loud. Then there's this SYK-like model that's similar to the MFT at high temperature that was solved by Antoine Olivier and company, where they put some random Heisenberg exchange, and they get this phase diagram, and at the quantum critical point, they get a linearity of the resistivity at low temperature, and then other similar calculations there. And then this is the group of Cornell with Unakim, where in SYK models, again, they find the linearity. I mean, this is plotted in a way that shows that the slope does not change very much with temperature. So back to high temperature. Why do we have a linear temperature dependence? Well, Wassim explained that earlier. And it's not because of scattering. I mean, the conductivity by Nernst-Einstein relation is proportional to compressibility times diffusion constant. And you saw the experimental results. The diffusion limit is consistent with the Mathieu-Rigel limit, which says that the mean free path can be shorter than the atomic distance. And the compressibility as this shape. So there's a saturation here, and then the compressibility is this way, and they have some funny behavior that is far from their asymptotic limit, but nevertheless, the product keeps the linearity. So in the general case, this is the expression for the conductivity in the Lyman representation. Yeah, in the Lyman representation. So I would just, I mean, this was noticed by a number of groups that when the temperature is larger than the largest energy, let's say the bandwidth or U, then all the temperature dependence drops out from this. So it's just proportional to these matrix elements. And this prefactor has nothing to do with the scattering rate. It's related actually to detail balance. So that's another way to get this linearity and resistivity. Okay, now I want to switch topic. Talk about entanglement, entropy, and mutual information near the Mott transition. So it was done by Kathleen and Giovanni at the Royal Holloway, Patrick Simon at BNL, and David Poulin in Sherbrooke. So we know, you know this, this phase diagram for on cluster dynamical mean field theory, 2 by 2. You get this first order transition. And here we have the so-called Widom line that is a crossover, which here it's just calculated using the inflection point of the dependence of the double occupation on U. So this was motivated by experiments on cold atoms that measured entropy and short-range correlations in the two-dimensional Hubbard model. So what we will look at are the first order nature of the transition, universality class of the endpoint, and crossovers emanating from the endpoint. So the techniques that I'm going to show now have been used in the context of quantum critical or finite temperature critical points by a number of people, but never in the context that I'm going to describe. So first, let me talk about single site entanglement entropy. What is that? Single site entanglement entropy for fermions is described as follows. You get a subsystem, let's call it subsystem A, which is obtained by tracing over the rest of the system. That gives you the so-called entanglement entropy. How can they measure that and how can we compute this? Well, here the density matrix is in the occupation number representation is just diagonal. It's a probability of being empty, singly occupied, or doubly occupied. So if you know this, you can compute the entanglement entropy for a single site. Now, do we know this? Yes, because we can experimentally or theoretically get double occupancy, which is this probability. Then this one is just the difference between the occupation and double occupancy. And finally, the probability of being empty is just 1 minus all the other ones. And it turns out we will also measure entropy, not only entanglement entropy, but thermodynamic entropy. So how can we do that numerically and even experimentally? It's using this Gibbs-Duhem relation. So using this Gibbs-Duhem relation, you see that if I put dt equals to 0, I can get the pressure by integrating the occupation number, which I know as a function of chemical potential. This is the chemical potential at half filling. And the entropy is just the derivative of the pressure with respect to temperature at constant chemical potential. So this is this entropy. This is the first experimental result I show. Entropy and the entanglement entropy, actually both quantities. In red is the entropy. And in fact, this maximum you can get, I mean, not the details, but you can get by very, very simple counting statistics. So the theory is the open circles and the experiment are the red points. The temperature is very high, 1 in units of T. And the entanglement entropy, so U is 8.2 here. The entanglement entropy is the blue symbols. And again, the filled one are experiment and the calculated one are the filled symbols. Okay, so now let's lower the temperature somewhat. It's inaccessible to experiments for now. The first thing you see for single site entanglement entropy, you start from log 4 at u equals 0, and or roughly log 4, and you end at log 2. So that's not a surprise. But on the other end, you get some sort of inflection point here, right? So what happens to this inflection point as you keep decreasing temperature? So here we plot the blue curve again, and this is a blow up of this region. And now what you see is that you have a first order transition when the temperature is low enough, and that's just the Mott transition. Now, if you take the derivative of the single site entropy with respect to U, well, it depends only through double occupancy. And we know that double occupancy scales like U minus U critical to the 1 over delta. So this derivative scales like U minus UC to the 1 plus delta. So if we draw now this inflection point in the single site entanglement entropy, we get the blue result, which as you see is very close to the other crossover that I described. So the so-called Widom line. So to summarize what I have to say about single site entanglement entropy, we can see in the single site entanglement entropy, the Mott transition, the critical exponents, that's usually not the case in the other circumstances, and the associated high temperature crossovers without knowing the order parameter for the transition. So the entanglement entropy, or one site is supposed to encode all the correlations between one site and the rest of the system, but there's another way to describe that. That's called mutual information. So what is mutual information? Take the entanglement, entanglement entropy for system A and for system B. So there's a region where, which is common to both subsystems. Now, if you subtract the entropy of the combined system, you see that you will be left only with this, which has been counted twice the first time around. So the entanglement, mutual information really measures how much of one system is known by the other system and vice versa. In this business, many people have looked at the area law, and that's usually what everyone does. I want to say this is not what we are doing, okay? I'm just looking again at how a single site is, as the mutual information of a single site and the rest of the system. It turns out that what is measured experimentally, even though they called it the mutual information, is not this. What is measured is the single site entanglement entropy minus the total entropy. So there's a way to rationalize this, which is to look at the total mutual information as it should be properly defined, like this, and then move to the case where we look at the entanglement entropy of this site with the rest of the system. And we don't count the first site because it has already been taken into account. In other words, we divide the system in 3 parts now. So we have this system in black, and then the rest in black, and we subtract, as usual, the union of this plus this. Now, if you look, these 2 things cancel. So as you move from one side to the other, in the end, you will be left with the quantity that I showed previously, which is the one side minus the total entropy. So these are the results. At high temperature, again, the experiment is the field symbols for various values of U, and the calculation are the open symbols. And in the calculation, our interest is to go to lower temperature. So these are the results. So let's start with high temperature. So that's the mutual information between one site and the rest of the system. and you see that the red filled symbols are the experiment, and the open is the theory. And again, there's agreement there, so we extrapolate to lower temperature, lower value of U, I'm sorry. And as we lower the temperature, then we find an inflection point at this. I mean, this is a blow up of this region with one additional temperature. And when we get to the mud transition, you see there's a jump here. Now you may be surprised by one thing, which is that the mutual information in the insulator at the transition is larger than the mutual information in the metal. That's surprising, no? Because the metal, the states are extended. So the systems know about each other much more than when everything is localized. So the way we explain that is that because in the insulator, you also have J that's there in these calculations. So that creates some correlations that you can see even in the insulator. But eventually the insulator, I mean, everything disappears. And that's the entropy in the metal and then in the insulator. And this dip here is related just to this, this maximum. So, and again, you can find the critical exponent in this single site mutual information. So, whoops, I was too fast. So this is this green, whoops. This green square is the place where you have this crossover in the mutual information. So all these crossovers are rather close to each other. So again, in the quantity that we call average mutual information, we see the mud transition, we see one critical exponent, and we see this associated high temperature crossover without knowledge of the order parameter. Now I have one thing to say, which is that one caveat is that all these calculations were done on the square lattice. And on the square lattice, at low temperatures, you won't see the mud transition, you would see antiferromagnetism. But the point is that in a sufficiently frustrated lattice, we expect that the crossovers at high temperature will be similar. So we don't expect, we are not encouraging experimentalists to try to do these experiments on the square lattice because all they will see is antiferromagnetism. Okay, so with this, I'd like to thank you for your attention.
Go to the podium.
So I have a question about this this part on entanglement entropy and the mutual information. So it's really nice you can do the calculation and so on, and see agreement with experiment. But so my question is, entanglement entropy or mutual information is new type of measure. And there are a lot of old problems on measures that have been around for a longer time. How does this entanglement entropy investigation give us new insight?
So the new insight, as I said, is that you see all these things related to first order transition and to exponents and to crossovers, without knowing what's the order parameter. I mean, and in this entanglement entropy and mutual information, in principle, you have all the correlations. So that's one thing. And then the other thing is that the importance of this Widom line that we've been emphasizing for all sorts of other crossovers is the same for this quantity.
In your slide, you had experiment and experimental point in the mutual information, only one, but no, the previous one.
Can you repeat the question?
Yeah, the question is, I saw in one of the slides on the mutual information that there was there was something about the experiment. How is that measured?
So the experiments, as Wasim showed, they can measure double occupancy by just looking at the system.
Yes.
If you know double occupancy, you know the full density matrix for single site.
Yes, but that's the entanglement entropy.
That's the entanglement entropy.
You also have for the
Mutual information was the entanglement entropy minus the total entropy.
I see.
And the total entropy, they also have to measure. And the way they measure it is really with using this Gibbs-Duhem relation. So every single point I have shown at half filling must be obtained by calculating all these points that are there, because you need to do some integral to obtain the entropy. So yeah, so to get 1 point on the curves that I showed, you need all these points there.
Now let's go to the metals.
Yes, André-Marie, very nice talk. I have a question about this mysterious discrepancy at high temperature between FTLM and the DMFT calculation. So am I correct that the two possibilities is either that for some reason the vertex corrections are important, even in that regime, and so that DMFT is more accurate for thermodynamic quantities but less for transport, or the other possibility is that this is a finite size system question with respect to FTLM. Can you clarify what you got from TPSC when you compared with and without the vertex corrections at high temperature?
Well, first, regarding FTLM, if you read the paper in detail, they have done lots of check for finite size effects. So they claim that it's not a finite size effect. Now, for the other question about TPSC, it's a method that should work only with up to intermediate coupling, intermediate interaction strength.
Yes.
But in fact, when you're away from half filling, and that the MUT physics is less important, you may expect that TPSC is not so bad. And in fact, it does reproduce the linearity, but the slope is wrong by a factor of 2. In fact, just as an anecdote, in the experiment, at the beginning, we had perfect agreement with the experiments, but then the experimentalist told us, oh, by the way, we just noticed a factor of 2 mistake. So anyway, so there's no agreement between theory and experiment on this.
No,
now,
but my most specific question is, if you do TPSC at high temperature and compare the results of the bubble to the full results with vertex corrections, do I understand correctly that they are identical?
Yes, you can see here, you see these bright spots are without vertex corrections.
Okay.
And the vertex corrections are very long to compute, so we cannot get them for all temperatures. But if you look at this point, which is sort of purple, and this point that's purple, and this point that's purple, they're all done with vertex corrections. And you see they line up really with the rest.
There are some questions that were asked in the Q&A section of the Zoom. So maybe, Turan, you would like to read them out loud?
Sure. So we have 2 more questions. The first one is from Paul Warm. Thank you for the beautiful talk. When calculating the vertex corrections to optical conductivity, were there any restrictions to a single channel in terms of 2-particle reducibility?
In the finite temperature Lanczos method, they included all the channels. Yes, in the sense that it's just they just compute the full current correlation function with all the intermediate states, so that includes all the channels.
And the other questions from Larry Belfiore. Is your entanglement entropy equal to the Boltzmann lattice entropy or Shannon information entropy? This
entropy that I call the S, this one, this S there is the thermodynamic entropy, and it is equal to the Shannon entropy in that case.
I believe there are no other remote questions.
Okay. Thank you very much.